Hello everyone, and welcome to our channel. In one of our previous videos, we discussed the physical principles underlying the device that is the cornerstone of modern electronics, the semiconductor field effect transistor. We also talked about how, with the help of these devices, or rather combinations of these devices known as logic gates, we taught computers to perform basic operations such as addition and subtraction. Today, we'll take a look at the physics of computers from a slightly different perspective and talk about how, from a physical point of view, a computer remembers, or in other words, how memory devices are structured in all their diversity, as well as why a computer needs a whole bunch of different types of memory based on various physical principles. Subscribe to the channel, and let's get started. Any memory device consists of cells, each of which typically stores only one bit of data, that is, one binary digit, which can have a value of either 0 or 1. And if we wrote 1 into our cell, then at the output, we should always have 1, regardless of the signal applied to the input, until we send a signal to the cell to rewrite the stored data, changing 1 to 0. And now our cell will always output 0 until we decide to rewrite it again. It turns out that memory cells can also be created from the same transistors, or rather assembled from transistors of logical cells. To begin with, let's consider the simplest transistor cell capable of storing information. For this, we will use the OR logical gate, which, as we remember, consists of just two transistors connected in parallel to each other. In short, I'll remind you that the OR gate operates in such a way that it passes current to the output if there is voltage on at least one of its inputs, or on both inputs at once. And 0, that is the absence of a signal, will only be at the output if there is no voltage on any of the inputs. So we have an OR gate, and all we need to do to turn the OR gate into the simplest memory cell is to pass the signal from its output to one of its inputs. Let's assume that at the initial moment in time, no signal is applied to the remaining free input. Accordingly, no signals are applied to both actual inputs, and we will also have 0 at the output. Now let's apply 1 to the input. Since this is an OR gate, it's enough for us to have 1 on just one input, and we will get 1 at the output. And this 1 from the output will now be passed to the second input. That is, both inputs of the OR gate will have 1, and the output will also be 1, even if we now disconnect the signal originally applied to the free input. That is, our modified OR gate has learned to remember whether we have previously applied a signal to its input. Essentially, we have created the simplest memory cell, which I congratulate you and myself on. But we have one small problem. If we want to rewrite the value written by us in the cell, then we cannot do this. In simpler terms, our cell does not support rewriting of information. It is somewhat similar to a torn-out sheet from a notebook on which something can be written, but what is written cannot be changed. We can only throw it away and take a new one. Dealing with computer memory in this way is, of course, impractical, and we need to improve the scheme somehow. There are several ways to do this, and here we will consider only one of them. For this, we already need two OR gates, each consisting, I remind you, of two transistors, as well as two NOT gates, with one transistor each, connected to each of the OR gates. I remind you that the combination of an OR gate and a NOT gate is called an OR-NOT gate, and its result will be exactly the opposite of the result of the OR gate operation. It will output 1 if both of its inputs are 0 and 0 in all other cases. Let's connect our OR-NOT elements in such a way, obtaining what is called an SR latch, from the English set reset. These are the names of the inputs of the resulting logic circuit. Let's say at the initial moment in time we apply 1 to the set input and 0 to the reset input, which means that we are writing 1 into our scheme. The first OR-NOT gate, I remind you, outputs 1 only if both inputs are 0. In our case, one of the inputs is definitely 1, that is, the gate outputs 0. This 0 is passed to one of the inputs of the second OR-NOT gate, and on the second of these inputs also 0, because we did not apply a signal to the reset input. 2 zeros at both inputs of the OR-NOT gate mean 1 at the output of this element and at the output of the entire scheme as a whole, which is what we need. In addition, this 1 will be sent to the second input of the first OR-NOT gate. This will not change the result, since if both inputs of the OR NOT gate are 1, the result will still be 0. But even if we now disconnect the set input, the result will not change. The first OR NOT gate will still output 0 at the output, forcing the second OR NOT gate to output 1. You may ask, where does the signal come from in the system when we don't apply anything? After all, a signal is essentially an electric current, and for something to flow out of the system, something must flow into it. And this is a completely correct and logical question. And the answer to it sounds like this. The current in the system is taken from an external power source, which powers our logic elements. Without external power, all this will not work. They say that the scheme is energy dependent, and we will return to this issue later. All right, now let's try to rewrite our cell. That is, change the value stored in it from 1 to 0. To do this, we need to send a signal to the reset input and see what happens in this case. The signal applied will reach one of the inputs of the second OR NOT element, and since now one of its incoming signals will be equal to 1, the outgoing signal will become 0. This signal will be sent to the output of our cell, as well as to the second input of the first OR NOT scheme. Now, on both of its inputs, there will be 0, meaning the signal outgoing from it will be 1. This 1 will go to the input of the second OR NOT element, effectively blocking it. Even if we now disconnect the signal we applied to the reset input, the result will not change. The scheme will output 0 until we apply a signal to the set input, indicating that we want to change the state of our memory cell back to 1, or until we disconnect the power, which will erase the data stored in the cell. SR latches are not the only transistor-based memory scheme used in practice, however. As I mentioned, our video is more about physics than about circuitry, so we'll probably limit ourselves to that. Memory based on semiconductor transistors has high operating speed. Both writing to and reading from such memory occurs at the speed of transistor switching, essentially with the same speed as the processor in our computer, capable of performing several billion operations per second, meaning it has a frequency in gigahertz. However, this memory also has its drawbacks. The key one is that, as we saw above, to create a memory cell containing just one single bit of data, we need a total of 6 transistors. To write 8 bits, or 1 byte of data, we would need 48 transistors, and so on. For example, the Windows 10 operating system constantly uses at least gigabytes of data, meaning 8 billion bits of data, for which we would need 48 billion transistors, which is comparable to the number of transistors in the computer's processor itself, and therefore, the cost of such memory storage would be correspondingly high. In reality, a modern computer needs much more memory, so it is obvious that even from an economic point of view, using only this type of memory is not practical. Furthermore, as we mentioned earlier, semiconductor memory requires constant external power, and it also has a relatively low data storage density, meaning that to store a large amount of data, we would need a device of relatively large size. Therefore, in modern computers, semiconductor memory, also called SRAM from static random access memory, stores only a tiny fraction of the total amount of stored data. It is used for the computer's own memory, such as registers, as well as for the processor cache. Registers store a very small amount of data that the processor is working with right now. It's like a spoonful of soup that we scoop up and prepare to eat. The cache stores data that the processor is currently working with or plans to work with in the near future. The cache can be compared to a plate of soup that we are going to eat for lunch. However, the majority of the soup is usually still stored in the pot. Similarly, the portion of data that the computer is currently working with is stored in registers. The data that it plans to work with in the near future is stored in the cache. And the main part of the data that the computer needs for operation is stored in the so-called main memory. And this information pot of main memory is organized on slightly different principles. Instead of 6 transistors per cell, here only 1 transistor is used, as well as 1 capacitor capable of storing a certain amount of electric charge. More precisely, when the capacitor is connected to a circuit with voltage, it accumulates charge, and then, when the voltage is turned off, it can itself become a power source, releasing the accumulated charge back into the circuit. We won't delve into the device and principles of operation of capacitors in this video. In the most superficial approximation, this is a well-known thing, and if you look more closely, there are many non-obvious things there, which probably deserve a separate video. In general, if you would like to see a separate video about capacitors, write about it in the comments, and I will definitely make one. Here and now, the main thing for us is this. If the capacitor is connected in a circuit with a voltage higher than the voltage it is charged to, it will draw some of the electrical energy and charge itself. If the voltage in the circuit is lower, the capacitor will release energy back to the circuit, discharging in the process. And it is precisely this property of capacitors that is utilized to create memory cells based on them. As a reminder, it consists of a capacitor and a transistor, as well as contacts connecting the cell to the circuit. More precisely, there are two of these contacts. One is attached to the transistor's gate, and depending on the presence or absence of voltage on it, it is determined whether the transistor controlling the cell is in an open or closed position. The second contact is connected to the line leading to the capacitor, and through it, reading and writing of data from the cell is carried out. The state of the cell, when it contains a 1, is considered when the capacitor is charged, let's say to a voltage of 1.2 volts, and if the capacitor is discharged, it means that a 0 is stored in the cell. To read data from the cell, we open the transistor and pass a voltage through the read and write line that is slightly lower than the voltage of the charged capacitor. Let's say let it be 0.6 volts. The charged capacitor has a higher voltage and will release the accumulated charge into the line, causing the voltage in it to increase, let's say to 0.8 volts. On the other hand, the discharged capacitor will start to charge, drawing energy from the line, causing its voltage to drop, let's say to 0.4 volts. So if after passing through the capacitor, we get a voltage higher than 0.6 volts, then we know that a 1 is stored in the cell, and if it's lower, then it's a 0. Now let's see how the write operation will look like. If we want to write a 1 to the cell, we apply a voltage of 1.2 volts to the corresponding line. This will charge the discharged capacitor, and the charged one will remain charged. To write a 0, we open the transistor with 0 voltage in the circuit. As a result, the charged capacitor will discharge, while the discharged one will remain discharged, meaning we will get a 0 in our cell, as required. However, capacitors have one problem. They tend to lose charge over time due to various reasons. Moreover, in our device, this process is exacerbated because during each read cycle, we drain a bit of charge from each charged capacitor and inject a bit of charge into each discharged capacitor. Therefore, for capacitor-based memory, a refresh procedure is also necessary, during which slightly discharged capacitors need to be recharged to the maximum, and slightly charged ones, contrary to our intention, need to be completely discharged. This data refresh procedure is in some sense a combination of read and write procedures. First, we determine whether a 0 or a 1 is stored in a particular cell by applying intermediate voltage to the line, and then we top up the capacitors in cells with 1s by applying full 1.2 volts to the line and empty the cells where a 0 is stored by applying 0 voltage to the line. After this, we can be sure that all capacitors that should be charged are fully charged, and all that should be discharged are discharged to 0. This refresh procedure occurs constantly, several thousand times per second, to ensure that we don't lose any data. The need to constantly update the information stored in capacitor-based memory determined its name, DRAM, or Dynamic Random Access Memory. The transistor cache memory, on the other hand, is called SRAM, which stands for Static Random Access Memory, as it does not require a refresh procedure. Of course, what we have just discussed is only a very general description of the principles underlying DRAM technology. For example, in this video, we will not discuss what SDRAM is, which stands for Synchronous DRAM, implying synchronization of the memory and processor clocks. To explain why this is done, we would need a fairly lengthy excursion, which lies more in the field of circuitry than in the field of physics, and this is not quite what we do on this channel. Let's just say that today almost all DRAM is synchronized, so when we talk about DRAM today, we usually mean SDRAM. Also, we will not delve into the differences between DDR standards, such as DDR3, DDR4, and DDR5, and so on. Perhaps it's worth mentioning that each subsequent generation of DRAM uses increasingly lower voltage, which positively affects the memory's power consumption. Instead, let's talk about why both types of memory, DRAM and SRAM, are necessary in our computer. DRAM has two main advantages over SRAM: price and data storage density. For example, a DRAM module will cost about 200 times less than an SRAM module of the same capacity and will have about 20 times smaller dimensions. These figures are quite conditional, as these devices rarely have even approximately comparable memory capacities. If we're talking about tens of megabytes of memory for SRAM, then in the case of DRAM, it's already about tens of gigabytes, which is 1,000 times more. So why not abandon expensive SRAM and switch to cheap DRAM? First of all, because it operates about 5 to 10 times slower. And if a SRAM is capable of providing data to the processor almost as quickly as it needs it, then when getting data directly from DRAM, the processor would spend most of its time idle, waiting for the slow memory to find the necessary data. That's why a compromise is made. Using a small amount of fast but expensive SRAM for the computer's operation, and a significantly larger amount of relatively cheap but slower DRAM, the data needed for the processor here and now is unloaded from DRAM to SRAM, just like you pour soup from the pot into the plate to eat. Another drawback of DRAM is its high power consumption because it needs to be constantly rewritten. And this becomes an even greater problem as larger amounts of RAM are used in modern computers and other electronic devices. SRAM consumes less power, but also requires constant power supply, and if you turn off your computer, the data will be lost. And obviously, this is unacceptable. You can't keep your computer, or even some of its parts, constantly turned on, so you definitely need some means to save data when it is turned off. That is, in addition to static and dynamic memory, we also need non-volatile memory. Typically, but not exclusively, this memory is used for long-term storage of data that we work with from time to time, and that may be needed by our computer in the future. If SRAM is like a plate of soup, and DRAM is like a pot of soup, now we're talking more about a refrigerator, or, for example, a cellar where we store potatoes, cabbage, carrots, and other ingredients from which we can make soup when we need it. And generally speaking, we have enough supplies of these products for dozens or even hundreds of pots of soup, but we don't cook it all at once, but use it as needed. Today, there are three main technologies for long-term data storage: magnetic storage, solid-state storage, and optical disks. The latter are practically obsolete today, so we won't spend time on them. As for magnetic storage, the most common type used in personal computers today is the so-called hard disk drive, or HDD. By the way, terminologically, it's not very fortunate. It's easy to think that a solid-state drive and a hard disk are the same thing, just different words. But no, they are fundamentally different technologies. On a hard disk drive, information is stored on small circular disks, usually made of a magnesium-aluminum alloy, assembled into small stacks. The surface of each disk is covered with microscopic concentric tracks made of a ferromagnetic material, usually a cobalt, chromium, and tantalum alloy. The tracks are divided into sectors, and each sector is divided into cells, each of which contains one bit of data, i.e., 0 or 1. Data is written by magnetizing cells in one way or another, making each cell a tiny magnet. If we look at the disk as if it were cut, the magnetization of the cell can be directed upwards or downwards. That is either inside the disk or outside. Between the unlike poles of the micromagnets in the magnetic cells, a magnetic flux arises, which we can register, determining how exactly the cell is magnetized. For example, we can agree that upward magnetization corresponds to 0 and downward magnetization corresponds to 1, or vice versa. However, this is not done today. The point is that between adjacent cells with opposite magnetization, a magnetic flux also arises, which we can register. But there is no such flux between identically magnetized cells. And it turned out that it is easier to register the presence or absence of a magnetic flux between neighboring cells than to determine the direction of the flux between the poles of the same cell. This means that we can register smaller magnetic fluxes, that is, use magnetic cells of smaller size, and as a result, achieve higher data density on the hard disk. That is, whether a 0 or a 1 is written on this part of the disk depends on whether the read head registers the magnetic flux between this and the next cell. That is, the data carrier is not the cells themselves, but the boundaries between them, which are also called domain walls. If there is a wall, then the magnetization of the cells differs. Then we record 1. If neighboring cells are magnetized the same way, then there is no domain wall, and we say that 0 is written. Additional reduction in the size of cells and increase in data density can be achieved by using supersensitive read heads based on the giant magnetoresistance effect. And relatively recently, the capacity of hard drives has been further increased by improving the recording method through the introduction of the so-called heat-assisted magnetic recording, or HAMR. If the first hard drives from IBM, weighing about a ton, could store only 5 megabytes of data, then their modern descendants can now accommodate tens of terabytes or tens of trillions of bytes of data with more than modest sizes and, most importantly, cost. The history of which technologies exactly allowed hard drives to go such an impressive path may deserve a separate story. And if you want to hear it, again, don't forget to write about it in the comments. Hard disk drives have impressive data storage density at a relatively low cost and also serve as non-volatile memory, meaning that the data written on them is preserved even after power is turned off. However, they also have their drawbacks. The key one is speed. While even relatively slow DRAM provides data transfer speeds of around 5,000 megabits per second, hard disk drives offer about 100 megabits per second, which is roughly 50 times slower than DRAM, not to mention the faster SRAM. Therefore, it's essentially impractical for the processor to directly read data from the hard disk, as it would be unimaginably slow by processor speed standards. Instead, the computer first loads the required data from the hard disk into the RAM and works with it, and after completing the task, the modified data is rewritten back to the hard disk. On the other hand, non-volatile memory is needed not only for storing user data. The processor also has a certain amount of data required for its operation, which would be useful to preserve even in the absence of power, meaning there was a need to create non-volatile main memory, an analog of SRAM or at least DRAM in terms of speed, but capable of retaining data even when power is disconnected. Initially, so-called ROM, read-only memory, was used for these purposes, meaning memory accessible only for reading. As the name suggests, data written to such memory can only be read but not rewritten. In ROM microchips, data was written at the factory and could not be changed thereafter. This was not very convenient for many reasons, so the concept of pure ROM was abandoned. First, the so-called PROM, programmable read-only memory, was created, which could be programmed but only once, like being able to write data only once to our simplest memory cell made of one OR gate, as we started the story. Then EPROM, erasable programmable read-only memory, was created, which could even be erased and rewritten, but through various clever methods, such as exposing the microchip to ultraviolet light. Finally, the EEPROM, electrically erasable programmable read-only memory, technology emerged, and the pinnacle of non-volatile internal memory evolution became flash memory technology. Currently, it has practically displaced all others, and thanks to certain technological advancements, it has even penetrated into other areas initially not intended for it, and today the successors of the first flash memory chips successfully compete with hard disk drives. How does flash memory work? It also relies on field effect transistors, but not ordinary ones, but slightly modified ones, so-called floating gate transistors. So, what is a regular field effect transistor? Essentially, it's a piece of P-type semiconductor with 2 pieces of N-type semiconductor embedded in it. Contacts are connected to both N-type semiconductors, leading to our circuit. In addition, another contact, called the gate, is brought on top of the region between the N-type semiconductors, which is necessary to control the transistor. A layer of dielectric, or insulator, is placed between the gate and the semiconductor. In the P-type semiconductor, the main charge carriers are positively charged holes, although there are also some electrons present. In N-type semiconductors, on the other hand, these functions are performed by electrons, although holes are present in them. Since the charge carriers in semiconductors of different types are different, Our semiconductor assembly will not conduct current just like that. But if we apply a voltage to the gate, creating an electric field directed downwards, that is, attracting electrons and repelling holes, then something interesting will happen in the region of the p-type semiconductor between the two n-type semiconductors. All, or at least most of the holes will be pushed out from there, while a few electrons from the entire semiconductor will, on the contrary, be attracted to this area. And although holes dominate in the p-type semiconductor as a whole, in the narrow area under the gate and between the n-type semiconductors, an area will be created where electrons will dominate. That is, the narrow layer of p-type semiconductor will turn into an n-type semiconductor, and electric current will be able to flow through it. It is said that the transistor will be opened. Now let's take a look at what a floating gate transistor is. Essentially, it's the same thing, but with an additional conductor inserted between the actual gate and the semiconductors. In the normal state, it doesn't affect anything. By applying voltage to the gate, we can still open the transistor, and by turning it off, we can close it. But what if we somehow introduce a certain number of electrons into this intermediate conductor? Indeed, when we apply voltage to the gate now, the field will still attract electrons from the p-type semiconductor and repel holes, attempting to create an n-type conducting channel. However, now this process will be hindered by the electrons in the floating gate, which will repel electrons and attract holes. In other words, do exactly the opposite of what the voltage applied to the gate is trying to do. The transistor won't open, or more precisely, to open it, we need to apply a higher voltage to the gate. So our device will operate differently depending on whether there are electrons in the intermediate conductor. If they are present, the transistor will remain closed even at the voltage that would open it if they weren't there. Thus, by placing and removing electrons from the gap between the gate and the semiconductor, we can change the state of the system. If there are no electrons, the current will flow at the working voltage on the main gate. And we say that a 1 is written in the cell. If electrons are present, then at the same voltage, the transistor remains closed, no current flows, and we say that a 0 is written in the cell. So essentially, we've described how the read operation from a memory cell consisting of a floating gate transistor will look like. We apply the working voltage, let's say 3 volts, to the gate and contacts and check if current flows. If it does, it means there are no electrons in the floating gate, and a 1 is written in the cell. If the current doesn't flow, it means that the electrons in the floating gate hindered the creation of a conducting channel, and a 0 is written in the cell. Now we just need to understand how we can place electrons in the isolated floating gate and remove them from it. That is, how the procedure of writing information to the cell occurs. Let's assume that a 1 is written in it, that is, the floating gate is empty, and we need to fill it with electrons, writing a 0 to the cell. To do this, we apply a high voltage to our transistor, let's say 10 volts. In this case, current will flow through the transistor as usual, but the high voltage on the gate will attract electrons from the channel so strongly that some of them will jump from the channel to the floating gate. How is this possible, you may ask, since the floating gate and the conducting channel are separated by a layer of insulator that electrons cannot pass through? And this is the right question, and the answer to it lies in the phenomenon known as the tunnel effect, a quantum mechanical phenomenon that allows particles to sometimes pass through barriers standing in their way. More about the tunnel effect, by the way, we had a separate video, the link to which will now appear in the upper right corner of the screen. And in this case, thanks to the fact that we applied a large electric field, some electrons from the channel will be able to tunnel into the floating gate, filling it. And since the tunnel effect is purely quantum mechanical phenomenon, not having an explanation from the standpoint of classical physics, it can be said that familiar flash drives and other similar media are a vivid confirmation that quantum mechanics works, no matter how strange its laws may seem to us at first glance. All right, we've filled the floating gate with electrons, rewriting the stored 1 to 0. How do we now perform the reverse operation and remove electrons from the gate, turning 0 into 1? Well, essentially the same way, Only now we need to apply voltage in the opposite direction so that it pushes electrons out of the floating gate. Of course, thanks to the same tunnel effect. And what's remarkable is that our floating gate is isolated from other parts of the cell. And to influence the number of electrons in it, we need to apply significant voltages by the standards of microelectronics. And if such voltages are not applied, then there is simply nowhere for the electrons from the floating gate to go, which means that the cell will retain the information written in it even when power is turned off. That is, the memory created based on such cells will be non-volatile. More precisely, over time, electrons will leave the floating gate thanks to the same tunnel effect. However, without an external voltage, they will do so very slowly. The floating gate can retain charge, and the cell, the data written in it, for years. Furthermore, to store one memory bit, we only need one transistor, as opposed to 6 in the case of SRAM, making flash memory cheaper and providing it with a higher data storage density. However, a downside of this technology is that writing and rewriting data requires significant energy consumption, meaning while reading data from flash memory can be done easily and fairly quickly, reading speed is in nanoseconds, similar to SRAM, writing poses a problem, taking microseconds, which is roughly 1,000 times longer. Additionally, each write cycle damages the insulator layer separating the floating gate and the semiconductor, so flash memory has a limitation on the number of rewrite cycles. However, since flash memory was originally intended for storing data relevant to the processor that was not expected to be frequently rewritten, this wasn't a major issue. There are various ways of connecting flash cells into arrays of data, called NOR and NAND structures, but this is more about circuitry than physics, so we won't delve into that. Instead, let's talk about how further development of flash technology has significantly expanded its application area, allowing the creation of devices for long-term data storage. The well-known USB flash drives, memory cards, and SSD disks, that is, those solid-state drives we mentioned. This was made possible by the discovery of a way to write more than just one bit of data to a single memory cell, unlike in other cases, but rather 2, 3, or even 4 bits. As we've already discussed, a flash cell with a 0 written to it differs from a cell with a 1 in the amount of electrons stored in the floating gate. If there are few electrons, the cell stores a 1, and if there are many, it stores a 0. But why should we limit ourselves to just the categories of few and many? Why not try to measure how many electrons we've pumped into the floating gate? And it turns out, we can easily do that by applying different voltages to the main gate of the transistor. Indeed, let's say there are practically no electrons in the floating gate, which means the transistor opens with the minimum voltage. We'll denote this state as 1, 1 in binary notation, or 3 in decimal. If at this voltage the transistor remains closed but opens with a slightly higher voltage, it means there are electrons but not many. Then we'll say that a 1, 0 is written to the cell, or 2. If we need even higher voltage, it means there are slightly more electrons than in the previous case, and we'll say that a 0, 1 is written to the cell, or simply 1. Finally, if in this case the transistor remains closed, we'll conclude that a 0 is written to the cell. And please note, instead of 1 bit of data, we now store 2 bits in a cell, meaning we can write not only 0 or 1, but numbers from 0 to 3, doubling the cell's capacity. Such cells are called multi-level cells, or MLC flash. If we increase the voltage step, we can achieve further capacity increases. For example, we can make on our voltage scale, still opening the transistor 8 divisions, 1, 1, 1, or 7, with the minimum opening voltage, 1, 1, 0, or 6 with a slightly higher one, 1, 0, 1, or 5 with an even higher one, and so on, up to the state of 0, 0, 0, or simply 0 when the transistor cannot be opened even with the maximum voltage used. This would be a triple-level cell, or TLC. There are also quadruple-level cells, or QLC, storing 4 bits of data, meaning one cell can store numbers from 0 to 15. However, the price for this is a decrease in memory speed, an increase in power consumption, especially during writing, and an increased probability of errors, both during writing and reading. Nevertheless, the game is worth the candle. Thanks to the use of this technology, it was possible to achieve a data storage density comparable to that of hard drives, meaning two different devices of approximately the same size can store roughly the same amount of information. Moreover, even slowed down due to the multi-level data storage system, SSDs still significantly outperform hard drives in performance. Another advantage is the absence of moving mechanical parts, which means not only no noise, but also a lower probability of errors and breakdowns. However, the latter is somewhat offset by the fact that the service life of SSDs is technologically limited, and they degrade every time they write information. However, hard drives still retain one key advantage over solid-state drives: significantly lower cost per unit of storage. 1 gigabyte on an SSD at the time of this video costs at least 1.5 to 2 times more than 1 gigabyte on a hard drive. Therefore, today we are gradually forming what can be called a 4-tier data hierarchy. Registers and cache memory on the fastest, but also the most expensive SRAM, main memory on slower and cheaper DRAM, a system hard drive for storing the operating system and main programs, SSD, and a working disk containing the main volume of information, HDD. And here, according to the plan, I should start talking about the technologies that are currently being developed to replace those mentioned above and how they can improve the current state of affairs. However, I look at the clock and realize that this story is probably better off postponed until next time. After all, if done properly, it won't be short at all, because there are many memory technologies being developed. They are all different, and many of them are very promising. So subscribe to the channel to make sure you don't miss the next time. Don't forget to like the video if you enjoyed it, and see you next time on our channel.